This conference will now be recorded.
Hello everyone. So today we'll start aromatic part of the hydrocarbon. So this slide we have already finished in the last class, but still I will start from this slide because this is the starting point where we will talk about hydrocarbons, aromatic hydrocarbons. So we have finished already alkane, alkene and alkyne. That is CC triple bond, CC double bond and CC single bond. And now we are having a completely different type of hydrocarbon which is aromatic hydrocarbon. Okay, which is it is also having a different name, and that is arenes. So after finishing this primary idea about aromatic hydrocarbons, next we will see the structure of the benzene ring. There is different features related to this benzene ring, and once we finish that, then we will start the nomenclature of different types of benzene derivatives. Fine. So aromatic hydrocarbons or arenes, arenes are aromatic hydrocarbons. That means it is not just hydrocarbon, there will be an aromatic character attached to it. Now the term aromatic, as the name suggests, aromatic means what? Something related to aroma. Now it is basically originally referred to the pleasant smell given off by some arenes. But now this term that we use nowadays, it implies actually a different types of delocalized bonding. It is not just delocalization of electrons that you see in any other type of molecules, but it is something different. Okay. So when I'm saying that it is showing aromatic property or it is showing aromaticity, which is basically a property shown by some molecules, that means there will be some special features in its bonding, and that is related to the delocalization of electrons. So that is the reason we use this term aromatic, not for the actual reason. That is, the original reason is because of the pleasant smell, but nowadays it is not for the pleasant smell. It is because of presence of some important features. That is the criteria the molecule must fulfill. Then only you can call them as aromatic compound. So benzene is the simplest aromatic hydrocarbon. And if you talk about the next simplest one, that will be C6H5CH3. So C6H6, it is basically having this type of structure. Obviously, we'll go into the details of this structure, but right now this much is enough. This is C6H6. As you can see, total 6 carbon atoms are present, and with each carbon, there is total 3 bonds you can see. That means one more bond must be there, and that is fulfilled by this carbon hydrogen bond. So this is the simplest structure of aromatic hydrocarbon, and the next simplest one will be methyl benzene, where one of this hydrogen now it is replaced by some methyl group. So that is the next simplest structure possible. Now here this formula that we have written C6H5CH3, that means this part is C6H5. Initially it was C6H6 because you have total 6 carbon atoms and total 6 hydrogen atoms, but now one hydrogen is replaced by CH3, so that is why this part is equivalent to PH group and this methyl group is CH3. So you can write it as PHCH3 or you can write it as C6H5CH3. And when it is simple benzene ring, it is basically PHH, because now this CH3, in that place we have hydrogen, or you can write it as simply C6H6. So both are actually correct. Now these compounds are circularly structured organic compound, which is clear from the structure, and it contains sigma bonds along with some delocalized pi electrons. So these three are basically the pi electrons. And all these 6 bonds, CC bonds, they are actually the sigma bonds. Okay. So both sigma and pi bonds are present. And because of this pi bonds, presence of these pi bonds, we get delocalization. The aromatic hydrocarbons are unsaturated hydrocarbon. Now that is already clear from this picture because we have some CC double bonds which have one or more planar 6 carbon rings, and these 6 carbon rings, as you can see here, it is a benzene ring, and these to which hydrogen atoms are attached. Total 6 hydrogen atoms are attached. Now this ring is highly unsaturated because if you look at the carbon hydrogen ratio, it is 1:1. So very high number of unsaturation. And in most of the reactions of aromatic compounds, the unsaturation of benzene ring is retained. So when not in today's class, but another class when we actually discuss its chemical properties, then you will see that these CC double bonds are actually not taking part in the reaction. Only this carbon hydrogen's bond will be broken, or that is, if there is any other group, that group may be replaced by some other group. This type of reaction will happen. But the basic structural part, that is, I'm talking about this part, it will remain intact. So the CC double bonds will not be taking part in reaction. And what is the reason behind it? The reason is that these CC double bonds are very, very stable. So they don't want to destroy their stability. So the stability must be maintained. And that is the reason the CC double bonds, they do not take part. And this is the cause of its special kind of stability. That is the aromaticity property. When it is present, there is some extra stability we expect from these molecules. Now the next structure, if you add one more ring to this benzene, you will get structure like this. So now how many carbon atoms are there? 6 already in the benzene ring and 4 more carbon in this. And total, if you count the total number of hydrogen, you will see 5 hydrogens are already there and 4 hydrogens are there. Okay, so in this way you can put, if you want to write the full structure, it will be something like this. Fine. So this ring is called naphthalene. Similarly, I can also add one more ring, that is a third ring also I can attach. Now the structure will be, so you can see the position of the double bonds are in such a way that delocalization is always possible. Now what I mean by this statement is that you will see that any two double bonds, whenever you choose in this molecule, they are always in conjugation. That is, in between two CC double bond, you will not find any sp3 hybridized carbon. So all these carbons are here sp2 hybridized. There is no sp3 hybridized. And that is the reason conjugation is always possible. So suppose I am considering this CC double bond. When it is shifted to this position, now obviously this CC bond, it must shift to the next position. That means conjugation is happening. Same thing you can also do for any double bonds. Suppose I am considering this double bond. When it is shifting to the next position, these double bond will be shifting here. So in this way, the pi electrons, they can change their position, and that is actually the delocalization of pi electrons. Now here you can see some pictures, and this naphthalene structure I have already done in the previous slide. This is anthracene. Now here something is mentioned as benzenoid. Benzenoid, it is mentioned beside naphthalene, and also beside anthracene it is mentioned as benzenoid. And this is tricyclic, this is bicyclic. Now this molecule is actually also aromatic, but this is not benzenoid. It is non-benzenoid. This is bicyclic. Now these three structures, though we are discussing hydrocarbons, and you may think that these are not hydrocarbons, and yes, you are right, these are not hydrocarbons. These are actually containing some heteroatoms. Oxygen is present, N is present, sulfur is present, but still just want to give you some information, and that is why these structures are shown here, just so that you can differentiate between benzenoid structure and non-benzenoid structure. So there are examples of aromatic hydrocarbon which do not contain benzene ring, but instead contain some other unsaturated ring. For example, these 4 molecules. So these 4 molecules are basically non-benzenoid. Only the first 2, number 1 and 2, these 2 are benzenoid. But the rest of the 4 molecules, out of these 6, they are actually not benzenoid type of molecule. But still these molecules have some aromatic character. Now the next question arises, how I will understand that they are showing aromatic property. Now we will learn about it just after a few minutes, that what are the conditions. If those conditions are fulfilled, then only you can call the molecules aromatic. And it is not necessary that any aromatic molecule, they always there must be some presence of benzene ring. It is true that in naphthalene you have presence of benzene ring, 2 benzene rings are there. Here 3 benzene rings are present. But to show aromaticity, it is not necessary that you always have to, there should be the presence of aromatic ring. And that is why there is 2 types of molecules. Benzenoid, they can also be aromatic. There is also non-benzenoid. Non-benzenoid means where a benzene ring type of structure not present, but still these molecules are aromatic. So they are non-benzenoid, but still aromatic. So this is the difference between benzenoid, non-benzenoid. So when aromatic compounds containing benzene ring, then we will call them as benzenoid. But if there is no presence of benzene ring, we will call them as non-benzenoid. So here from this structure, it is clear. Okay. Now, after in the next slide, not in the next. Okay, let me see. Not in the next slide. Probably we will be able to finish it today. There we will see the features. What are the features to show for a molecule to show aromatic property? Then you will be able to understand why tropone molecule is showing aromatic property. Why, sorry, here piperidine is not aromatic. Why this molecule is showing aromatic, that we will study. But before that, you have to know the criteria to show aromatic property. Okay, after that, now we have some initial idea about aromatic hydrocarbon. The next thing that we will study now is structure of benzene. Now, why, remember in case of alkene and alkynes also, we have seen the special characteristic of its structure. That is, under alkene, we have seen the structure of ethylene. Under alkyne, we have seen the structure of acetylene. And now when we are talking about aromatic hydrocarbon, we will talk about the structure of benzene, which is the simplest aromatic molecule you can think about. Now here, point-wise, we will discuss its structure. First, we have here the molecular formula. Now, how we will approach when discussing this topic, that is structure of benzene, just forget about the structure that I have shown. Yes, it is true that benzene is having this type of structure, but suppose you do not know this structure. So what we will do, point-wise, we will do some discussion. As you can see here, first point is molecular formula, second point is behaviors like saturated compounds. So there will be some points, we will discuss those points. Once we finish the discussion, then you will be able to understand how gradually we are approaching to prove that yes, benzene is having this type of structure. So we will talk about some evidence, some experimental observation, which on the basis of which we can say that yes, benzene is having this type of structure. Okay, so let's start from the molecular formula. Elemental analysis, which is a process by which you will be able to understand what is the molecular weight, what is its molecular formula. So elemental analysis, it helps us to understand its molecular formula and also the molecular weight determination. So from this analysis, it is observed that this is the formula for benzene ring. Again, I am saying just forget about the benzene structure. Suppose you do not know anything. Then you just know that, okay, this is the formula. 6 carbon atoms, 6 hydrogen atoms. Now, one thing from this formula is clear, that it is highly unsaturated because the carbon-hydrogen ratio, if you see, it is 1:1. When carbon numbers are very high compared to hydrogen, it means that gradually unsaturation is increasing. Just think about the alkane, where the general formula we use CnH2n plus 2. Then when we move to the next category, that is alkene, then the formula becomes HnH2n. Then when we move to alkyne, then the formula becomes 2n minus 2. So what you are seeing, one thing is clear, when you are moving from more unsaturation, because here you have CC single bond, here you have double bond, here you have triple bond. So when you are moving to more unsaturation, the number of hydrogens compared to carbon, it is decreasing. So this is also same thing here. Carbon and hydrogen, from this ratio, we can say that unsaturation is very high in the benzene molecule, whatever its structure. So this molecular formula does not match with alkane, alkyne, or alkynes, because if you want to match with any of these general formula, you will not be able to do so. So that is the reason. Though it is also true that for aromatic compounds, aromatic hydrocarbons, this type of general formula is not possible, right? It is only for alkane, alkene, and alkyne. So one thing is clear here, that this molecular formula, once we know this from elemental analysis, one thing we can say confirmly that it is not matching with alkane, alkene, or alkyne, right? Go to the next one, that is behaviors like saturated compound. So this heading, it means that benzene, it shows some behavior which is like saturated compound. But here also we have mentioned just that it is having a very high amount of unsaturation. But now we are saying that its behavior are saturated compounds. So it is a little confusing, right? But don't get confused. There's nothing to get confused. It is actually because of its unique character. So gradually we are moving to the structural analysis. So just observe the points one by one. Try to focus on the points, whatever we are discussing. So we already know what is this molecular formula. It is C6H6, fine. It is not matching with alkene, alkyne, alkene. Okay, done. Next one, behaviors are like saturated compounds. That means it will show behavior like alkanes because only alkane is saturated. Alkene and alkyne, they are unsaturated. So behavior is like saturated compounds. So what is happening here? In spite of being unsaturated compound, it doesn't undergo addition reaction. Now, when we say that a molecule is unsaturated, that means there is double bond or triple bond. What we expect? We expect that there must be some addition reaction where CC pi bond is broken and two new sigma bonds are generated. This type of reaction you have seen many times in case of alkene and alkyne. But now, what we are seeing that it doesn't undergo any addition reaction. But instead it undergoes substitution reaction. But substitution reaction is the characteristic of the alkane. That is the characteristic of the saturated compound. But still we are having this type of observation. So that is why we are saying the heading is behaviors like saturated compounds. Now one very common reaction for alkene and alkynes we have seen that reaction with bromine. So when bromine is added to CC double bond or CC triple bond, what happens? Two CBr bonds are formed, and as a result, the color of bromine, which is reddish brown, that color is discharged. And this reaction we use as identification test. That is to check whether a molecule is having any unsaturation or not. But now, when we are trying to add bromine solution, what we see, there is no reaction happening, no product. That means still the bromine color is present. It is not discharged. So this is the observation. So when treated with bromine in presence, now this observation is in presence of CCl4. That is a reagent, that is bromine CCl4 solvent we use when we do the unsaturation test for alkene or alkyne. But suppose you are treating benzene molecule with bromine in presence of some trace amount of catalyst, which is FeBr3. Now what is happening? Benzene is forming monobromobenzene. That means one of these hydrogen is now replaced by Br. But that is not addition reaction. That is actually substitution reaction, where hydrogen is simply substituted by bromine atom. Look at this reaction. C6H6, one bromine will be taken by this hydrogen and hydrogen will be removed. So the formula is now C6H5Br. And this reaction is happening in presence of FeBr3. So now we are just talking about the observations. What is the reason behind it? We will go to that point later. Right now, just focus on the observations. So it is not behaving like saturated unsaturated compounds. Rather, it is behaving like saturated compound, like alkane. And we know in case of alkane, no question of addition reaction. What you get mostly, you get substitution reaction, and that is also we are having here, right? Now, this type of observation suggests this is possible only if it has cyclic structure of 6 carbons, each containing one hydrogen atom. That means when it is cyclic structure, 6 carbons are it is forming a ring, and each carbon is having one hydrogen. Then only this type of reaction is possible. Because now, why we are saying so? Because from this reaction, it is clear that any of this hydrogen you can replace by Br. That means all the hydrogens are equivalent. Because if all the hydrogens are not equivalent, you should get different types of C6H5Br. But that we are not getting. We are just getting one type. That means all the hydrogen atoms are equivalent. And equivalent structure is possible only if it is cyclic. Because if it is not cyclic, there will be terminal position, there will be middle position, and then you cannot say that all the hydrogens are equivalent. It is possible only if it is having some cyclic structure. So from these observations, we can reach this conclusion that it can have some cyclic type of structure, not open chain like alkene or alkyne. Now the third observation is observations that suggest that there is presence of 3 CC double bonds. It is observed that when you do some reaction, that is, you have taken benzene, you are treating it with Raney nickel or platinum, which is basically metal catalyst, and also you are adding hydrogen gas. So what you are trying to do, you are trying to do hydrogenation reaction. Remember, hydrogenation reaction we do in presence of metal catalyst. So you can take either Raney nickel or you can take platinum or palladium at this temperature, and we are getting cyclohexane. So when we treat benzene at this temperature, we treat it with hydrogen gas in presence of some metal catalyst. What we get? We get cyclohexane. Cyclohexane is this structure where there is no unsaturation. That means if this is your product, the initial substrate, and per mole of benzene there is 3 moles of H2, or if you say in terms of molecule, 1 molecule of benzene. 1 molecule of benzene requires 3 molecules of H2. That means there must be 3 CC double bonds. Otherwise, why the ratio is 1:3? Okay. So this type of CC double bonds must be present. So this is again confirming the cyclic structure of benzene. In present, another reaction, look at this, in presence of sunlight and in absence of Lewis acid catalyst like FeCl3, AlCl3. Benzene adds 3 molecules of chlorine. That means 1 molecule 3. So it is 1:3, just like the previous reaction. Now it is important to mention that in absence of Lewis acid, because if you are treating benzene with halogen in presence of FeCl3, or if you are treating it with that is chlorine with FeCl3, or you are treating bromine with FeBr3, then you get monosubstituted product, which we have seen in the previous slide. Remember? So when you use this type of catalyst and you are treating it with bromine or FeCl3, Cl2, we get substitution. But when you are treating again halogen, you are treating with benzene, and but now you are not using any Lewis acid catalyst and you are doing the reaction in presence of sunlight. Now the reaction is different. It's 1:3, and look at this. All the carbons are present, all the hydrogens are also present, but there is 6 chlorine atoms included. Now, what type of reaction this can be? It is possible only if all the CC double bonds are gone and there is presence of, there is presence of 6 chlorine atom. 6 chlorine means total 6, 3 Cl2 means total 6 chlorine. Now, though we have said that addition reactions are not, we do not get, but remember, it is not that we will never get it, because here you are seeing addition reactions on. And if you are treating it with 3 hydrogen, then you will get cyclohexane. But now addition reaction is happening because the reaction condition is very drastic. You are doing the reaction in presence of sunlight, you are doing it in presence of very high temperature. So under normal condition, that when the reaction condition is not very drastic, then there is no addition reaction, only substitution. But only when you are using some drastic condition or some special condition, then only these CC double bonds are broken and you get addition reactions. Okay, try to understand the difference. Under normal condition, no addition reaction, only substitution. But if you are using drastic condition, you can get addition reaction, as you can see in these 2 examples. One more reaction is reaction with ozone. So C6H6, you know, in case of alkene and alkyne, you have seen how it reacts with O3. There is formation of some ozonite. Now, is it possible with benzene also? So with benzene, what happens? 3 O3 molecules, they are attached with benzene. Carbon hydrogens are still there. But these 3 O3 molecules, when when it is attached to it, the formula is like this, but what is the actual molecule, actual structure of triazonite is this one. This is 1:3. If you consider the mole ratio or the ratio of molecules, then we are getting this type of benzene triazonite. So 3 ring formation. So original, these are the position of the double bonds. If I consider the original position double bonds, these are the double bonds. So this type of addition reactions under drastic condition, it suggests that yes, there is 3 CC double bonds. Otherwise, how you will get this type of structure? Suppose you already know the structure after the experiment. You already know its structure. Now you just from the observation try to move back to the substrate. Obviously, the substrate should have this type of ring structure, because with open structure you cannot get cyclohexane, you cannot get C6H6Cl3, you cannot get benzene triazomate, right? After number 3, the fourth point, very important. Here, Friedrich August Kekule suggested that these 6 carbon atoms are benzene. They are joined together by alternate single and double bonds. And in this way, they form hexagonal ring, and each carbon is further connected to hydrogen atom. And this structure we have already seen, right? But remember, if we suggest this type of structure, there are actually 2 objections. Now, what are those objections that we have to understand? So what he is saying, Kekule is saying that 6 carbon atoms joined together by alternate single and double. That means if you consider the ring, first there is a single bond, then you will have double, again single, double, again single, then double. But if you consider this type of structure, there are 2 objections. Now, what are these objections? The first objection is that suppose if I am saying that a single and double bond alternate, and there is 2 substitution. A may be any group, and that is arbitrarily you can consider anything. Now, when benzene ring is disubstituted, that means 2 similar type of substitution is present. It can be in 2 different ways. It can be in the X format or Y format. So when it is X format, in between these 2 carbon, which 2 carbon? To which these 2 groups are attached. These 2 carbon, in between them, there may be double bond. Or the substitution can be another way, where in between these 2 carbon I am only highlighting because these 2 are attached to a group. Now there is single bond present between these 2 carbon. But that means when you are having any disubstituted benzene, there should be 2 types of isomer, right? If you are considering this Kekule explanation, he is saying that there is alternate double or single bond, and their positions are fixed. So if the position is fixed, I can also do some numbering. Suppose let me put some numbering 3, 4, 5, 6. So 2 types of substitution possible, either between 1, 2, 3, 4 or 5, 6 in X format. So in this case, all the CC bonds are having double bond. Or it can be in another way, where the A groups are between 2 carbon. It is either 1, 6 single bond, 2, 3 single bond, or 4, 5 single bond. So that is another isomer possible. But actually, experimental observation suggests that there is only one type of disubstituted product. Only one type of disubstituted product. So that means what? This X and Y, there is no such 2 isomers. There is only one type of disubstitution what we are getting. So this is the objections we are facing, right? So how to get rid of this? That is how to explain that why it is not happening. So first objection is that you will get 2 types of isomer, but the second but that is we are not actually getting experimentally. We are getting only one type. Now how we will explain this? To overcome this objection, now Kekule suggests that benzene was a mixture of 2 forms, where the double bonds have oscillating nature. So this is that is to overcome these objections. That is, we are not getting 2 isomers. We just get one type of molecule, one type of. There is no such isomer. Now to explain this, Kekule is now saying that there is some oscillating nature. That means the position of the double bonds. As you can see in the X structure, position of double bonds are 1, 2, 3, 4, 5, 6. But the positions are not like this. They can shift their position. That is, from 1 to position, they can shift to 2, 3. That is said by Hückel. But even with this modification, Hückel's structure of benzene fails to explain unusual stability of benzene, preference to substitution reaction than addition. So what the last statement means? So up to this point, it is understandable that he is saying that the double bonds, they are changing their positions. They are changing their positions. That means initially, if the double bonds, their positions are like this, now they can change their position. So in the new structure, you will get, now the positions are like this. So what is, as there is some oscillating nature, they are always changing their position. So how we will get two types of isomer, only one type of isomer. So up to this point, it is fine. But it is also observed that benzene ring, if you simply consider this type of three double bonds, the stability that we expect from these three separate CC double bonds, that stability we are actually not getting. We are getting some higher stability than that. So if you consider that the position, there are three double bonds, you expect one type of stability. But from benzene molecule, the stability that we are getting, that is far beyond that. So there is some unusual extra stability of benzene we are getting. And that we cannot explain if we simply consider this type of oscillating double bond. And another point is, there is always a preference for substitution reaction. It is true that the double bonds, they are changing their positions, they are oscillating in nature, but still we should get some addition reactions, but that we are not getting. We are getting it only under drastic condition. But substitution reaction we are getting very easily. That means these CC double bonds are having some kind of nature because of which the cleavage of these CC double bonds are very, very difficult, and that is why you are not getting addition reaction. You are getting preferentially substitution reaction. So still there is some explanation required, so that we can say why we are getting this type of unusual stability and why there is so much preference for substitution, why addition reaction is not happening even if the double bonds are shifting, but still there is CC double bonds, they should undergo addition reaction, but that we are not getting. Okay, now to explain this, you have to next you have to take the help of resonance description. So first of all, try to understand resonance, that we have already done in the chemical bonding chapter. There we have seen what is resonance. So in resonance, two or more than two Lewis structures can be drawn for a molecule. So just take the example. Suppose I am drawing butadiene. So this is butadiene 1, 2, 3, 4. 1, 3 butadiene. So in this case, I can draw its resonance structure by shifting the double bond. So if I shift the double bond from 1, 2 position to 2, 3, the new resonance structure we get is like this. And at 4 carbon, there will be negative charge. And as you have shifted these pi electrons from 1 carbon, there will be some positive charge. So this is resonance. And in this resonance, try to see here only the electrons that are present in the pi bond. These electrons are basically shifting their positions. But we have not changed the position of carbon. They are still there. We have not changed the position of hydrogen. They are still there. There is still two hydrogens before or after. So positions of hydrogen we have not disturbed. We are just changing the position of the electrons. So they differ in the position of electrons, not in the relative position of atoms. When we draw in general, any resonance structure, when we draw, this is the criteria. Actual structure of the molecule is said to be the resonance hybrid of various possible alternative structures. So in this case, 1,3-butadiene, as you can see, do not think that structure 1, this is the actual structure, or structure 2, that is the actual structure. No, none of these are actually the true structure. The actual structure is hybrid of these two, as if average of these two. So something, suppose number 3, which is not exactly like 1, which is not exactly like 2, it is something in between. Fine. In between means what? This 1, 2 position, it is not fully double bond. And in the structure 2, these 1-2 positions, now they are single bond, but you cannot say it is completely single bond type of nature. So there will be some double bond nature, there will be some single bond nature. So that is why it is the resonance hybrid. It is at the average structure of these two. Now in this molecule, I'm talking about 2 structure, but it may be more than 2. And you have to take the average of all the structures, possible structures. In benzene, Hückel structures 1 and 2 represented the resonance structure. So this is 1 and 2. So in structure 1, if I am numbering these positions as 1, 2, 3, 4, 5, 6, the double bonds at 1, 6, 4, 5, 2, 3. But now, obviously, it is changed. And number 3 structure, it is the hybrid of these 2 structures. So Hückel structures 1 and 2 represent resonance structure, but when you have to consider the resonance hybrid, which is structure 3. So these 2 structures exist only in theory, and the actual structure of benzene is the hybrid of these 2 hypothetical resonance structures. So these 2 are hypothetical resonance structure. So though whenever we write any reaction with benzene, we write benzene molecule in this way, where you can see separate double bonds. And sometimes you are bound to do this, because when you have to show some mechanism how the double bonds are taking part in reaction, then you have to draw it. There is no such way. Though it is true that they are not the actual structure is the hybrid of these 2, but still, for the sake of showing mechanism, sometimes you have to draw it. You can also draw benzene in this way, where there is a circle. Now this circle is basically means the pi electron cloud, because the pi electron cloud, they are all over the 6 carbon atoms, and that is the reason we can also draw benzene molecule just by putting a circle. So both these structure, whether you draw it with 3 separate double bonds or simply use some circle inside the ring, both are fine. None of them are correct. Sorry, incorrect. Okay. So number 5th point, we now know what is actually happening. So it is not exactly structure 1 and 2, because if you consider a separate structure 1 and 2, there is still some CC double bonds. But when you consider the resonance hybrid, now what I can say, just talk about this. If we talk about this 1,6 bond, it is, if you consider structure 1, it is having double bond character. If you consider second structure, it is having single bond character. But none of these statements are actually correct. It is having character which is not exactly double bond, which is not exactly single bond. Fine. Next observation is spectroscopic measurement, and now it will be very clear from this bond length, CC bond lengths. So it is observed from X-ray spectroscopic measurement that benzene ring is planar in nature, and that is expected because all the carbons are sp2 hybridized, and all the CC bonds are equal length. So which means what? That sometimes they are having double bond character, sometimes they are having single bond character. It is something in between. So it is not exact, that is a normal average value of CC bond, that is not present. Normal average value of CC single bond, that is also not. So this 1.4 angstrom value, 40 angstrom value is something in between. So this bond length lies between CC single bond, which is having, this is the average bond length, 1.54 angstrom. See, this value is high, and if you consider pure CC double bonds, it is 1.34. Now this value and these 2 value, it is something in between. It is not so high like CC single bond and so low like 1.34. So again, it proves that the CC bonds are having not exactly double bond character or single bond character. The absence of pure CC bond, CC double bond in benzene ring is actually responsible for its reluctance to show addition reaction when there is normal condition. It is possible only under drastic condition. So now it is clear to us why addition reactions are so uncommon, because there is some no pure CC double bonds, and also there is very special unusual type of stability which we are going to discuss now next. Because of this extra stability, benzene will try to maintain its stability, and that it can do only if it can avoid addition reaction, because if it is undergoing addition reaction, the CC double bonds will no longer be intact and stability will be gone, but that is not desired. Fine. So next we will see the molecular orbital structure. Now to understand it, first we will see the hybridization sp2. So let me write the sp2 hybridization. So we know there is outermost electronic configuration 2s2 2p2, but when it is in excited state, one electron from s, it will go to p orbital. And if it is undergoing sp2 hybridization, that means after mixing this, after mixing this s, p, p. Now this p is pure p. It is not part of hybridization. It will be responsible for pi bond. But now after mixing this, we are getting total 3 sp2, right? Now this 3 sp2, it will form sigma bond. One sigma bond will be with carbon atom. Another sigma bond that will also be with carbon. Another sigma bond that will be with hydrogen. Now try to understand the structure. So let me consider any of these see. So just focus on this carbon. So this carbon is having, there is also carbon hydrogen bond, don't forget it. So this is a sigma bond with the next neighboring carbon. This is a sigma bond with another neighboring carbon. This is a sigma bond with hydrogen. That means total 3 sigma bonds. All these are by this sp2 hybridized orbital. And there is also a presence of pi bond. So this CC pi bond that will be formed by this pure p orbital, which is not taking part in reaction. So in this way, for each carbon, now you can understand how it is sp2 hybridized. Now this pure p orbital, it will be remaining perpendicular to the plane of benzene ring. So if benzene ring is on the plane of the screen, then hydrogens, that is this p orbital, it will be perpendicular to the plane of the screen, right? So hybridization is clear. Now we will see the molecular orbital structure. So see here all the p orbitals, this is the benzene ring, this is in plane, okay? And these pure p orbitals, they are perpendicular to it. So sometimes there is CC single bond, suppose here, here and here. Or in the next moment, it can change its position. So this is when it is in average, this type of cloud lying above and below the benzene ring plane will be there. So this delocalization makes the molecule very, very stable than the hypothetical cyclohexatriene. Cyclohexatriene is this molecule. Now, if you are thinking why I am calling it cyclohexatriene, why I am not calling it benzene? Because understand the difference. When I am saying it is cyclohexatriene, which is basically hypothetical, it doesn't exist actually. So you will call it cyclohexatriene only when the CC double bonds, their positions are fixed and the CC bonds, they are having some pure double bond character. But in reality, that is not the case. That is the difference with benzene ring. These double bonds are always changing their positions. You have to consider this type of pi electron cloud above and below. And when there is pi electron cloud above and below the plane, it is no longer cyclohexatriene, where the position of double bonds are fixed in their positions. But now it is not so. So this is the difference between these two molecules. One is hypothetical cyclohexatriene and benzene. So if it is simply cyclohexatriene, you will have two types of bond length. You will have CC double bond length, which is around 1.34, and you will have CC single bond, which is 1.54. But none of them you are getting. You are getting the average value. So this is the difference with hypothetical cyclohexatriene. Unlike alkene and alkyne, benzene undergoes substitution reaction rather than addition. in bracket it is mentioned only under Drusty condition. So under normal condition, addition reaction. So now it is understood that this pi electron cloud, it will try to remain intact. Only this carbon, hydrogen, or if there is any other substitution, that will be taking part in reaction. So this H can be substituted by some other groups. Otherwise, there will be no reaction. Now look at this picture. Your idea about this unusual stability of benzene, it will be clear. So look at this molecule. Here we have cyclohexane with 1 cc double bond. And if this is energy in the y-axis, that means higher is the position of molecule, higher is the energy. Now this is the position of simply cyclohexane. That means it is minimum energy somewhere here. Now when it is having a cc double bond, now the position is here. Now this distance is 28.6 kilocalorie. Similarly, when there is 2 cc double bonds, it is further having some more energy. That means gradually stability is less. 55.6 kilocalorie. So this is the difference between cyclohexane and cyclohexadiene. This is cyclohexene, only one double bond. This is cyclohexadiene, 55.6. Now it is interesting. If you simply multiply 28.6 by 2, you get this value. That means one double bond 28.6, two double bonds 55.6. Similarly, when you multiply 28.6 with 3, by considering as if there is 3 separate cc double bonds, now you get the value which is 85.8. So this 85.8, when you multiply 28.6 by 3, because for one double bond it is 28.6 kilocalorie energy extra compared to cyclohexane. So when there is 3 double bonds, it must be 28.6 into 3, 85.8 kilocalorie extra energy compared to cyclohexane, which is in red color. And when you reduce it with 3H2, it is converted to cyclohexane. Now look at the position of benzene. The benzene position is somewhere here. If you extend the line, it is somewhere here, as if in between cyclohexadiene and cyclohexene. And the difference, this is if this distance is 85.8 and this distance it is 49.8. That means if you subtract from 85.8, if you subtract 49.8, you get this energy, and that is equal to 36 kilocalorie. So this amount of extra energy is lost by benzene. It is not present in benzene, and that is why benzene is proceeding towards more stability, closer to cyclohexane. So if there is no such electron cloud, it is simply cyclohexatriene where addition reactions are expected, then the energy should be 85.8. But actual energy observed, it is 49.8, which is 36 kilocalorie lesser than the hypothetical cyclohexatriene. And as it is having this extra stability, that is, this amount of energy is not present. That is why it is more stable. Higher energy means what? Unstable. Lower energy means what? Stable. So this amount of energy it is not having, that is why it is more stable. And this is called resonance energy. So resonance energy means when you subtract the actual hybrid structure from the most stable theoretical structure, that energy difference is resonance energy. And when resonance energy is very high, that means the molecule is basically gaining more stability. It is directly related. So 36 kilocalorie resonance energy benzene ring is having. Fine. This is number 7 point, and now we have reached, we have already identified the structure of benzene. Now we can start the aromaticity, and to understand aromaticity, basically it is based on Hückel's rule, right? So when you know what is Hückel's rule, based on that you can predict a molecule whether it will be aromatic or not. And based on this, questions are very common. So we have to study very well. The term aromatic can be applied to all the ring systems, whether or not having benzene ring, if some conditions are fulfilled. So it only depends on some conditions whether it is fulfilled or not. It doesn't matter whether the molecule is having some benzene ring or not. It is not important. Only just these rules must be fulfilled. Now it is this knowing this aromaticity and what are the Hückel's rule. Don't think it is only important for hydrocarbons. It is not just. Sometimes what may happen, you may also get some organic molecule where it may be that it is not hydrocarbon. It is having some heteroatom oxygen or nitrogen. But you can get those questions in the exam, and it will be asking whether this molecule is aromatic or not. You have to identify. So it is not that it is always hydrocarbon. It may be some containing some heteroatom also. So when you know the rules exactly, you can apply it to any molecule. Not necessarily it has to be any hydrocarbon. Okay. Now what are the rules? Hückel proposed that aromaticity is a function of electronic structure, and a compound will be aromatic if following conditions. There are actually total 4 conditions that must be obeyed. Then only you can call them aromatic. So these are the conditions. The first condition, the molecule must be planar. Okay, because when we talk about aromaticity, it is all about the stability because of delocalization of electrons. And delocalization of electrons is only possible if the molecule is planar. So by chance, if it is not planar, how the delocalization will take place? That is why it must be planar. Then the molecule must be cyclic ring structure. Then the third point is complete delocalization of pi electrons in the ring. So the ring structure that we will have, it may be 6-member, 5-member, whatever. Full delocalization in the complete ring, there should not be any obstruction. So suppose there is some sp3 carbon in between two sp2, then there will be some block. Then delocalization is not possible because with sp3 hybridized carbon, how delocalization will be there? So it is not that only delocalization must be present. Obviously, electron delocalization should be there, but it has to be full conjugation, full delocalization in the whole ring. And the last most important point is presence of 4n plus 2 pi electrons in the ring, where n value is any integer, 0, 1, 2. So when you put n value equal to 0, 4n plus 2, what you get? 4n plus 2, putting n value equal to 0, you get 2. Next, when you put n equal to 1, you get 6. Next, if you put n equal to 2, you get 10. That means, see how it is proceeding. 2, 6, 10. When this number of electrons are involved in delocalization, it is not that the electrons has to be from any double bond only. It may be from any lone pair also. We'll see the pictures. Don't think right now it may be some, you can have some lack of clarity, but when we'll actually draw the structure, we'll try to understand how these tools we can apply. It will be clear, don't worry. So see how it is moving, 2, 6, 10. So when we are having this number of electrons, then you can also move to this next one, that is when n equal to 3, it is 4 into 3, 12 plus 2, that is 14. So the next value will be 14. So the gap is basically 4. 2 to 6, 4 gap, 6 to 10, 4 gap, 10 to 14, 4 gap. So this type of number of electrons must be involved in the delocalization. Now two important extra terms also you have to know. When you learn aromatic molecule, you also have to know what is anti-aromatic. Now for anti-aromatic also, all the rules are basically same, just like you have seen these 4 rules. Only if the last rule, it will be replaced. 4n plus 2 will be replaced by 4n pi. Otherwise, the first 3 conditions are as it is. Now, when it is 4n pi, try to understand difference. N value 0 means this is 0. 4n pi is equal to 4 when n value is 1. 4n pi is n equal to 2, it is 8 pi electron. So here also it is proceeding by gap of 4, but now it is 0, 4, 8. In this way it will move. You can also move to the next one. It will be 3 into 4, 12. So when it is moving in this gap 0, 4, 8, they are basically anti-aromatic. And anti-aromatic compounds are very, very unstable. Just like when some molecule is aromatic, we say that it is having extra kind of stability. Similarly, when there is some molecule which is anti-aromatic, it will be very unstable. One more term is also there, and that is non-aromatic. So non-aromatic, its stability is in between. It is not so stable like aromatic compounds. It is not so unstable like anti-aromatic compounds, but it is something in between. And how you will understand? When you will call a molecule non-aromatic, if any of these 4 conditions are not fulfilled, it will be non-aromatic. So for example, mostly you will see a molecule is non-aromatic if all these 3, that is 2, 3, 4 points. Now the 4 points may be 4n plus 2 or it may be 4n plus any of these. So mostly we'll see only the first point is not maintained, and then only we have to call the molecule as non-aromatic. That is a planarity condition when it is not maintained. Suppose rest of the things are okay. It is cyclic, there is some full conjugation, there is 4n plus 2 electrons or 4n pi electrons, but the first point is not maintained, or any of this point. I'm not saying first point, but mostly it is observed that the first point is not maintained, and ultimately we had to call it non-aromatic because planarity condition must be present. Fine. So these are the conditions for to call a molecule aromatic, and we also have learned now what is anti-aromatic and when you will call it non-aromatic. And next we will discuss some examples based on which we can say that yes, this is the way by which we can apply these rules to understand whether a molecule is aromatic, non-aromatic, or anti. And question based on this is very common. It is very important to understand these two. But here remember one thing as note. Usually it is observed that ring compounds containing 7 carbon atoms, because it has to be cyclic. So when it is some cyclic structure and up to 7 carbon, then mostly it is planar. But whenever it is 8-membered ring or 9-membered ring, planarity may not be there. Okay. Now the ring size is high and the rigidity is less. When the ring size is high, the rigidity of the ring is lost. Now they can have some non-planar structure. Fine. So some examples we'll discuss in the next class, and we'll try to see how we can apply these rules. And any species, if it is given, not necessarily hydrocarbon, we'll also see some heteroatom containing molecule, though that is not hydrocarbon, but still from exam point of view it is important for us to understand all different types of molecules to categorize them as aromatic molecule, anti-aromatic molecule, and non-aromatic. That we'll do in the next class. Thank you for listening. We are ending the session here.